Okay, everybody hear me okay? I imagine so. Okay, so shared memory parallelism in Julia. If anybody was at JuliaCon a couple of years ago, you may have seen some conversation about this, because we've been working at it for a while. I'm going to start. I mean, this is a very basic question, but the question does arise: why threads at all? Why can't we just do everything with processes and messaging? And that's a reasonable question in the past, but no longer so, because folks may have heard of the Knights processors and greater than 200 threads available on a single processor. At times like this, your memory per core reduces to the point where you literally cannot do anything useful with a process per core, per hardware thread. So you pretty much need threads, which is essentially shared memory parallelism. And that gives you typically quicker performance, less communication requirement, and you reduce the memory needed by your application. But of course, as we often know, shared memory parallelism always opens you up to a vast host of dangerous programming errors, which is sort of the cost of doing business. So again, early principles. We'll partition parallelization according to these two broad domains. There are many other ways to categorize things, but in essence, there's task parallelism and data parallelism, and with task parallelism, it's the sort of thing that you would possibly do in Apache or some other server application where you'll use a thread for different functional units in the program. And those functional units may run as a pipeline, or they may have overlapped execution, but essentially the code that different threads are running is different. This doesn't naturally scale. If you throw in a few more cores into your processor, it's not straightforward to figure out what you're going to do with the extra threads. Whereas data parallelism, and of course with task parallelism, because different code is running, the reasoning about interleavings of threads is much harder. Synchronization is the real challenge to getting things right with a task parallel program. Data parallelism, on the other hand, is a lot simpler in many, many ways. It's basically applying the same operations to a very large data set. And this is what most high-performance computing codes do, not just within a processor, but across multiple processors, multiple nodes. We're talking about really vast data sets for like weather models or particle simulations or all sorts of things. It's a little bit easier. Correctness is not quite as hard because all the code, all the threads are running essentially the same code, and the partitioning of the data across the threads is pretty regular often. But that's always not always true. Most codes are like this. So in essence, we want all sorts of parallelism capability within Julia, but these are the broad categories. So we started a couple of years ago in 2015, 2016, adding threads to Julia. Now it's been really hard. We started with the simplest possible approach, which is just a parallel loop. So you could do what it shows over there, and as it says, we got a rapid speedup. Very easily just by adding the macro prefix at threads to the for loop. And this will work today now. And it required a lot of work under the scenes, under the covers to make this actually work correctly, making the code generator, garbage collector, everything thread safe. So we've gotten to that point now. And it's time to evolve beyond the basic model to real threads in Julia. And this talk is really about how that's going to look, essentially. So with the previous, I should repeat, with the previous threading infrastructure, the experimental stuff, we had a number of successes. We were able to show all sorts of really interesting things. In particular, the second item over here is accepted for publication recently. We joined the petaflop club with Julia, reaching 1.5 dual precision petaflops on Cori with the pure Julia code. So these are a whole large bunch of Knights Landing processors, and this was some real science that NERSC was interested in. And this successfully demonstrated stability in parallelism across a very large number. I mean, at 1.3 million threads, you get pretty much every interleaving possible. So if there's something wrong, it's going to show up at this scale, and we found that it was reasonably stable. So from this previous work, we learned that loop parallelism is pretty good. It does pretty much what we need on many, many, many codes. And so all we need is basic task parallelism functionality, and that gives us every possible parallelism interface that we could possibly require. And so we know this already because Cilk did this a long time back. Cilk gave us spawn, sync, and parfor, and they say and have shown that you can write pretty much any parallel code with just these three primitives. And for Julia's philosophy of productivity and easy to use, this seems like the way forward. And so this is essentially what we are providing going forward, is the equivalent of spawn, sync, and parfor. What we also found in the process of doing the experimental threading infrastructure is that the problem is not so much adding threads to Julia. The problem is making them useful at all levels of the language. Julia in particular uses a lot of packages, a lot of your function. It's not just Julia, any high-level language, MATLAB, R, what have you. A lot of your functionality comes from packages. If you want to parallelize code inside your package, which is essentially a library, you need a way to compose parallelism. And what does that essentially mean? That means that if I have parallel code in my application and I want to call a function which is all inside a library which is also parallel code, I need a way for this to actually work. Today, in pretty much every language out there, including C and Fortran, nesting parallelism does not work too well. Your inner parallel loop runs serially, whether you're using OpenMP, whether you're using the threading building blocks, or you're using Cilk, or I'm sure other things out over there. If you're using sequential implementations of your libraries, then whatever effort library writers put into parallelizing their operations, like I can attest to the vast amount of effort that groups at Intel have put into making their matrix multiplications code scale really beautifully. It scales really well. But you can't use that wonderful scalability as soon as you're using a parallel loop outside the gem call. So your performance is limited by the scalability of the outer loop. And this is how it's sort of illustrated. Now, this is an example, right? It's just to show what a task DAG looks like in parallel terms. Nobody is actually going to create a task for every iteration of this particular loop, but it's representative. And it's also correct in the correctness sense. This is a matrix multiplication code for n by n matrices. And if you lay out, as it shows here, your parallel on the outside, your parallel on the inside, and then your parallel at the third level as well, as long as you do a tree reduction, a sum reduction on the innermost loop over here. And if you lay this out in the form of parallel task DAG, this is what it looks like. For n equals 4, your outer parallel loop has 4 nodes, followed by the J loop, which has 4 nodes, and so forth down over here. You can see the reduction is represented by the joins from these nodes over here. Is this clear? Right? So if you run this sequentially, as without any of the parfors, I'm not sure if this will be very visible, so let's try. You can see the green dot show up over there, and it's trying to animatedly show you the sequence of execution of the tasks in the DAG. Was that visible to people? Yeah, yeah? Great. So that's essentially how this code is going to run if you ran it with just a single thread. right? And you'll notice that it is a depth-first schedule, which is kind of natural. That's the way calls work in programs. Right, and you need n-squared space to store all your intermediate results before you can do your final reductions. Right, so this is how you expect your serial algorithm to play out when you run it serially. Now, suppose you ran this with OpenMP, and it was actually a sensible thing to do because they're real tasks and not just a single multiplication operation. Then the way this would run is that your first par4 would start executing the top of each of those subparts of the graph, right? And then your second par4 will create 4 more threads, and your machine has only 4, so you have quadratic oversubscription of your threads. This, if anybody's ever tried to do this, will kill whatever performance you may have seen from any of your code. So obviously, nobody does this anymore. And in fact, you actually have to, nowadays, in the past, this is how it would work. Nowadays, you actually have to turn on this environment variable for OpenMP to do this because the default behavior is different. Right? Oh, the other downside of this approach is that your space requirement is much higher. So one of the alternate ways to do this sort of task scheduling, this sort of parallelism, is work stealing. Work stealing is very widely known, particularly here at MIT, thanks to Cilk. Work stealing is essentially a way in which tasks are scheduled, as opposed to the OpenMP way, which is essentially, here's a bunch of tasks, give them to all the threads. Work stealing has a queue per thread, and every spawned task is simply pushed to the queue. When a thread runs out of work to do, it starts stealing from other threads' queue. So every thread has its own queue, right? The point to essentially note over here is that spawned tasks are pushed to the bottom of the queue, right? This is a double-ended queue, so there's a top and there's a bottom, and every thread has one. So spawned tasks are pushed to the bottom of the queue, but when a thread runs out of work, it steals from the top of a queue. What this really means is, though people have in the past believed that work stealing solves the nested parallelism problem, what this really means is that this essentially runs serially, because whatever parallelism is available is used up in the outer loop, and the inner loop no longer gets any work stolen by other threads. So you really end up with exactly the same sort of problem as you do with OpenMP, right? And that's illustrated in this slide, hopefully. It's also clear. Where your first par4 uses up all 4 threads that you have on your 4-thread machine. At that point, there's another par4, but there are no threads available. So everybody runs serially from that point on. Right? So what this means is that your beautifully tuned library routine with a parallel loop in it is not actually going to run in parallel as soon as the user code has a parallel loop itself. So clearly this doesn't make anybody very happy. So there's hope. Right? There's a decade-old idea out of Carnegie Mellon called parallel depth-first scheduling, which theoretically shows very, very good time and space bounds for scheduling and better cache efficiency because it follows a depth-first schedule like your sequential schedule, so cache behavior is better. Of course, the problem is that the paper proves a bunch of guarantees, but it doesn't actually talk about implementation very much. And so for many, many years, there has not been an implementation. But we believe that, the reason I'm saying all this is because we believe we have one now, and that's what this whole thing is about, really. So with a parallel depth-first schedule, in the ideal world, this is what would happen in terms of execution of the task DAG. You get your first par4, and all the 4 threads start their work. As soon as you get your second par4, you want to go depth first. So you want to switch threads away to do this. Is that clear? You see the 4 green dots here, right? And then similarly, when you get the third par4, again you switch to go down depth first. Right? So you're still proceeding down the task DAG, but you're doing it in a depth first fashion. Right? So what that means is that your inner parallel loops have threads in them, even though you have parallel loops outside. So you get true nested parallelism if there was a way to accomplish this parallel depth first scheduling, which was not at all clear whether there was a possible implementation. So, okay. Right. So the implementation we have is you can look at it at that pull request and the discussion over there and the to-do list, which we've made great strides on this week already. This layers essentially on top of Julia's task system, and I assume at least the folks in this room are at least somewhat familiar with the task system, the coroutines that Julia has. We are leveraging that same abstraction, coroutine tasks, to describe tasks in the shared memory parallelism model. The key difference is that now tasks, rather than being pure coroutines with switching within the same thread, tasks are now can be executed by any thread in the system. As soon as you have multiple threads in the system, scheduled tasks could run on any one of those. So you'll use essentially the same interface, schedule, fetch, wait, yield, that are already there today in Julia, but they will map now to the parallel system. And we will add an interface for the parallel for, which is what we want primarily for the data parallel model. So the way we accomplish this, I'm not sure if people would care about the intimate details of exactly how this works, but yes, you are? Okay. So, so how do we essentially do this, right? So work stealing works with a deck double-ended queue per thread, right? We replace all those double-ended queues with a single priority queue that is shared across all the threads. So every thread, when it's looking for work, is essentially going to go hit that queue and say, hey, give me the highest priority work, highest priority task to run. And it'll run that task, right? This becomes challenging to scale. So how does that end up working is something I'll demonstrate in a foil further on. But suffice to say that if we simply specify task priorities on the basis of thread IDs, which means completely transparent to the user, it ends up giving us a depth-first schedule. So the priority queue will end up sorting tasks in a depth-first order, and as long as the threads are reading from getting their next task to execute from the priority queue, they will end up executing in depth-first order. The challenge becomes the priority queue itself, because a priority queue by definition has a highest priority item, and there is only one. And as we possibly know, at scale, at a very large number of threads, if everybody is hitting the same cache line and trying to steal or take the item at the top of the queue, this does not scale very well. It scales very, very poorly. And that's exactly what this is saying over here. The bottleneck is in the delete min operation, because there is only one such operation, only one such item, the minimum item. So one of the bigger challenges, apart from the insight about the task priority and the thread ID causing the ordering of tasks in a depth-first order, the other major thing over here was essentially how do we do this and scale it well, and that was the priority queue implementation. And we discovered this, multi-queues. Now, all scalable priority queues, and there's a whole bunch of them in the literature, all of them essentially relax the constraint on minimum. What's the highest priority item? That's the only way they can effectively scale. So the papers are cited over here. The graph shows you that it scales pretty well, even up to, I guess this is 60 threads. something like that. And they have a comparison over here for all various sorts of priority queue implementations, from ones that the spray list is a particularly involved design. It's one of the densest papers I've read, actually. So this is relatively straightforward. You simply create, given P processors, you create some C where C is 2 or 3, or that's the numbers they tested. Here they're showing results with C equals 2, C equals 4. You create that many sequential queues, which are essentially priority queues, essentially heaps, right? Insert will randomly select a queue and add an item over there, and delete min randomly selects 2 of the queues and returns the highest priority item among those 2 queues. And it turns out this works remarkably well because the rank error is linear in the number of processors. And so that's an acceptable rate of error. You're not going to get perfect highest priority, but in the parallel world, because happens before is very variable based on that particular run, machine timing, I/O operations, things vary. This is an acceptable margin of error. Okay, so given the priority, given multi-queues, and given the idea that a task priority is decided by thread ID, if you look back at exactly the same task DAG and try to follow this along in terms of how items get pushed into the priority queue, a parfor essentially is going to create a bunch of tasks and add them to the queue. The thread that is invoking the parfor will use its ID as the priority. So that is 0, right? These 4 tasks at the top level are priority 0. They will get executed first. The task on the left, the leftmost task, is priority 0 running from thread 0. The 4 tasks it creates will be priority 0. The 4 tasks thread 1 creates will be priority 1 and 2 and 3. So at the point that a bunch of tasks are created by the parallelism function, it will inspect the priority queue to see if there's a higher priority task to run. If it does, it suspends the current task and switches to that task. And that's what I meant in an earlier bullet. If this is sounding a little staccato, I apologize. This is not a very well prepared presentation, but that's what Q&A is for. So the ordering of the priorities you can see on the basis of the thread ID will end up with these 4 tasks here when they're pushed onto the priority queue having the highest priority, and therefore all the threads will switch to running the higher priority task. Now, this is not going to work across the board because we're not synchronizing at each spawn point. So we are not forcing all threads to go lockstep over here. So it is certainly possible that thread 1 will push its tasks into the priority queue before thread 0 gets to the point of pushing its tasks in the priority queue, which means thread 3 could end up running thread 1's tasks rather than thread 0's as it's supposed to. We can fix that by creating more lockstep synchronization. If that turns out to be necessary, it's perhaps something that we can add in the future, but this gets us pretty close to a true depth-first schedule, certainly closer than any of the existing solutions in this space. And what this essentially means is, at the end of the day, why is all of this important? This is important because if you write a Julia package and you spend some time and energy in making sure that your code is scalable and will parallelize, that functionality will get used by Julia applications. You're not going to find a situation where all that is running serially. And that's really the whole point that we're trying to address over here with this, why we're going to all this effort to try to get better performance from your Julia applications by getting better cache efficiency and better scalability. And that's it. That's my talk. Questions?
Is there something inherent about Julia that makes this easier than, say, taking the scheme and trying to enable it in other languages?
No. No. In fact, there is a plain C implementation on GitHub now that you can test and play with if anybody cared. And it was very easy to do. The integration with Julia, in fact, requires that we are much more careful about a variety of things like the garbage collector and code gen and synchronizing stuff. So it's, yeah, there's nothing, it's not restricted to Julia, but Julia is likely to be the first, hopefully not only, but first language to actually have a working depth-first, parallel depth-first scheduler. Sorry, Viral.
Slight interruption. I think we can take the food and then continue the Q&A.
Yeah, sure, sure. It's not a crowded enough room that we have to be too formal with it.